Welcome to Homework Lib.
Hey everyone. So this example is of a solenoid and you have been given certain values. I am going to take this for a general case. So I am going to use a lot of variables in this question. Now a solenoid is more or less a donut, and it doesn't have to be a circular solenoid which has a circular cross-sectional area. Now in the question what they're talking about, this area of cross-section is this, and I'm going to call it A. And the radius that is affecting this is measured from here, and I'm going to name it R. And you can see here the current is going and going around and round and round and coming back out from here. So if we are using the right hand rule, what can we say about the direction of this magnetic field? So if this is going this way, then we are bound to get a magnetic field like this, and this magnetic field will go all around the toroid, and then it'll come back here. So you can clearly see that this magnetic field is only bound within the volume of this circular tube or this donut. Now I'm going to give us some equations to begin the question. So first off, what can we say about the magnetic field of a toroid? And that is given in a very basic equation, that is B is equal to magnetic permeability times N, which is the number of turns. I is the current divided by 2 pi r, which is this distance. Now I can go into detail, but for now you have to believe me on these equations. The next up is the magnetic flux. What can we tell about that? Flux is usually how many field lines go through a particular cross-sectional area. Now in this case, we can say, I'll do the justice of writing the vector format, but we know that this B is given by this equation up here. So then we can plug this in here, Ni divided by 2 pi r. Okay, and then A is given, which is the area of cross-section, because all of these field lines have to go through this A. And then we can come up with an equation for self-inductance. Self-inductance is given by L is equal to number of turn times the magnetic flux divided by current. Now you did get an equation for the magnetic flux, and you might as well substitute it here. That is Ni divided by 2 pi r times A. Okay, and you can see I and I get cancelled off, and finally you are left with an equation of mu naught n squared A divided by 2 pi r. Okay, so what else is there? We need to come up with an equation for the energy stored, and I can go into detail, but for now the energy of an inductor, that is given by half L inductance times I squared, which is the current. Now in the previous example you have come up with an equation for L, which is if I may put it inside brackets, mu n squared A divided by 2 pi r, and I squared you can write it as it is. So this is the equation. Now what they're asking you to do is find the number of turns, right? And if you look closely, you have been given R, you've also been given A, you also know I, and mu for this instance, let that value be 1.25 times 10 to the power minus Henry per meter. And also the energy is also given. So in that case, if you may rearrange these terms, you will come up with an equation where 2u times, I can consider it as 4u. 4u times pi r divided by A mu naught I squared, and then it is equal to n squared, and then all I have to do is square root the entire thing, and I will get an equation for n. So n is equal to square root of entire thing, and that is how you find the value for the number of turns.